you. So my name's Chris Wales, and today I'll be talking about using SPH for modeling resin flows during the composites manufacturing process. So what we're really interested in looking at during the manufacturing process is the formation and the evolution of voids in the composites as the material is cured. So while sort of composites are typically sort of strong in plane where you've got the fiber direction, sort of the weaker out of plane where you're relying more on the matrix strength, and sort of having a sort of 1 to 3% sort of increase in the void content in your sort of matrix resin area can greatly reduce the interlaminar shear stress, and then this in turn sort of lowers your overall sort of mechanical properties by sort of 20%. So to get around this, you'd have to increase the amount of composites you use in your structure, which increases the cost and particularly weight, which we're interested in aerospace. So typically the best way of reducing the void content in sort of the composites manufacture is to use an autoclave. So the resin is cured under high pressure, and this helps reduce the void formation. But this is sort of an expensive way of doing it, and it also is trickier curing larger parts in autoclave. So ideally we would want to do out of autoclave composite processing, but these typically end up with a sort of higher void content. So what we want to do is look at modeling the sort of void evolution over the curing cycle, so then we can better understand what parameters affect it, and then we could sort of eventually look at sort of how we can more optimize out of autoclave composites to reduce the void content. So there are a few different ways of void formation in composite process. So sort of the main one we'll be kind of initially looking at is the sort of interlaminar sort of void formation. So typically you form the composites by stacking up layers of prepreg. So these layers of prepreg, the surface isn't smooth, as we can see from a sort of surface scan in the bottom left. And so as you stack these up, you get regions of air trapped inside between the layers. And then as you cure the composites, so I've got a video inside here. So we've got a bunch of prepreg layers stacked up on a sort of corner jig, and then there's a vacuum bag around the outside here. And then as we cure, so initially nothing happens, and then as you sort of start heating up the composite, the resin viscosity reduces, and then it begins to flow, and then most of the voids sort of consolidate at the beginning of, and then eventually so most of the consolidation done is fairly early on in the cure cycle. And so as we skip further forward, as the resin is beginning to cure, then you do get very little void movement. So there are a couple of other sort of void formation things which we're not particularly looking at initially. So there will be some off-gassing from the resin under temperature. And then there's also the prepregs. So ideally you have the fibers and then they come pre-impregnated with the resin, and it would be 100% saturated. But this doesn't always happen. So you get some areas of dry fiber where there is a low resin content. So what are the big challenge of modeling this with SPH. Hopefully it won't crash again. So challenges are we've got fairly long cure times and much higher sort of viscosities than sort of normally simulated during sort of SPH simulations. So we start off with a very high viscosity at the beginning, and then as we heat it up, viscosity rapidly drops. So although it's fairly low compared to its initial starting condition, we're still sort of in the 10 to 100 sort of Pascal seconds sort of range, which is a lot higher than sort of water. And then we have this low viscosity for a fairly long time. And this is where most of the void consolidation occurs. And then the viscosity starts going up, which is effectively as the resin begins to cure and sort of get cross-linking in the matrix. So the region we're primarily interested in is this sort of region here, where most of the void consolidation occurs. So as I said, sort of it's going to take occurs over several minutes, and we've got relatively high viscosities. So this is a problem for sort of standard explicit SPH. So what we've done is we've treated the viscous terms implicitly. So as we'll see, this allows us to have a much higher time step size. And then we also found that initially we started looking at weekly SPH, but we found that because during the cure cycle, they're effectively sort of compact. So this compaction sort of force acting on the composite meant we had to have a high speed of sound for weakly compressible SPH to avoid large density fluctuations. So this then impacted the time. We've moved to incompressible SPH. And then finally, because the flow is driven largely by the resin, which is incredibly slow moving compared to sort of gas change, we've modeled the gas phase on a background grid rather than using a SPH solver for the gas phase. And I'll talk about that bit. So this avoids having this smaller time step, the lighter gas phase, the overall simulation time step. So the main sort of approach, it's very similar to a standard sort of incompressible SPH solver. So we have calculate our sort of velocity based on the momentum equation without the pressure terms. So the main difference from the standard sort of ISPH is this is now solved implicitly. So we have one linearization there. So we've got our intermediate velocity. We then have the standard pressure pass-on equation solved. And then finally, put that pressure field back into the sort of equation and re-solve implicitly the velocity field at the future time step. Then we update the particle position. And then because we're doing this manually in both, we then resolve this at the new particle positions. We do this until the particle positions converge to within a tolerance over that step. And typically this takes 1 or 2 sort of complete ISPH loops. So for the bound conditions, we use sort of the Adami sort of extrapolated boundary condition. So here we have a force balance at the wall. So we're saying that sort of acceleration of the fluid close to the wall is related to the sort of pressure gradient wall, gravity is acting on the fluid, and the and then we have the additional viscous terms, which are typically left out of the this boundary condition formulation for lower viscosity flows, but they're quite important for getting the correct pressure, the moving wall cases for the high viscosities we're going to be using, and this then equals the acceleration of the wall. So going through extrapolating in the SPH form, the pressure of the wall is given by this expression here. So we have the pressure of the fluid particles, acceleration of the wall, acceleration of the fluid particles, and then a viscous term there over the kernel summation. And then we also extrapolate the fluid velocity to the wall velocity, and this is the prescribed velocity of the wall component. So in terms of sort of the actual SPH solver, we use a Reynolds C2 kernel, the laminar viscosity term by Morris, and then when we're doing a Cure cycle to match experiment, we have the we know the temperature, and then we know from that we have a model of the viscosity at that current time step. So then, so we know the prescribed Cure cycle temperature. We can vary the viscosity during simulation to match the correct viscosity at that point in the Cure cycle. So what we do is because we've got this implicit thing, we have 3 implicit solves, which are the number of particles, including the boundary particles, times the number of dimensions for the first velocity intermediate calculation, n by n system for the pressure solve, and then another n by d for the final velocity solve. And then we solve this using a preconditioned biconjugate gradient stabilized approach using the CU sparse CUDA library on a GPU. So these matrices are stored in a compressed sparse row format. And this is one slight drawback of doing it on the GPU is end up being a bit memory limited on the size of the problem we can use, because we have n by d number of equations, and then the off-diagonal terms are related to the number of neighboring particles. So then the n by d by number of neighboring particles are the number of particles we store. So this goes up pretty rapidly. So that's a bit of a limit on the total problem size we can look at. So for the gas model, we use a background grid, then we solve sort of an ideal gas law for each of these cells in the background grid. And then what we do is we have, as we move the SPH particles over the background grid, we sort of essentially say there is 0 gas mass in those cells, initialize the uncovered regions with a fixed mass. Then we move the SPH particles over them. And then if the gas cell is partially filled, we just change the density by the change of effectively volume fill of that cell. If a cell becomes completely covered, we move that gas mass into the neighboring gas cell. So this effectively sets a sort of time step limit, is that we can't have particles moving over one time step more than the grid spacing for the background grid. So once we've sort of adjusted the mass due to the volume change or mass covering a cell, we then have a averaging step over connected gas regions. So then we average the mass over the complete gas volume area. So we have a constant average density and then a constant pressure within each gas region. And then finally, we then turn the cells closest to the interface of the SPH into gas particles, which we then use to prescribe the pressure back onto the SPH solver. So first, we're going to look at a 2D test case of just the resin only. So this is a 2D blob acting under gravity. And then there exists a similarity solution for the asymptotic shape of the blob. So we've got a viscosity of 100 Pascal second, a delta T step of 0.1 seconds. And this is a sort of 10 centimeter radius blob. And then we can see, it's very cool, quick, but as it spreads out, we do match the analytical solution for the shape of the blob as time goes on very well. So as I hinted at before, most of the cases we're looking at aren't actually being sort of driven by gravity. They're being driven by effectively the force pressure difference across the vacuum bag. So to sort of validate this for a 2D case, have a triangular region of resin. And then this top wall here moves down to simulate this sort of effect of top bag. So we have a 10 millimeter initial height. Final height is 1 millimeter. Once again, 100 Pascal seconds. And there is a sort of analytical approximation for the sort of final achieved pressure for this case based on sort of Pascal flow assumptions. So we can see as we go through, basically sort of not a lot happens until we start approaching sort of the shape going from the triangle to this rectangular shape between the two pressures plates, and then we get the large increase in pressure. So we're slightly below the analytical solution, but we're much closer to the predicted pressure achieved with the same case run with a volume of fluid method. So, and moving to 3D. So in this case, we've got a cylinder of resin being compressed between two plates. So I haven't shown the top and bottom plates for this one. And then I've just removed half the particles. So we can see sort of the effective pressure evolution through the resin region. So yeah, we sort of get nice spreading out. We'll get the maximum pressure in the center there. Once again, got a sort of analytical approximation sort of based on Resin flow type behavior, and the analytical and SPH show very good agreement, SPH being slightly higher than the analytical. So this is a very similar case to the previous one, except now we've removed some of the resin from the center of the cylinder. And I haven't shown it in here, but this region is filled with the gas mesh there. And then as we sort of compress it, the gas volume increases, gas pressure increases in the center region, which then transfers onto the SPH, and we get a slight widening of the hole as the gas pressure increases. And then we've once again got SPH comparison to analytical result. Now, in this case, the maximum pressure, which corresponds to the pressure of the gas, is more noisy than it is in the pure SPH case. And this is because we've got a sort of very sort of small section height. So it's quite small volume, so it's very sensitive to volume changes. And so this is related to sort of how accurately we can sort of map the volume ratio of the overlapped region in a gas cell by the SPH cell. And we had to sort of introduce a small sort of cutoff value sort of at the minimum sort of overlap region to stop sort of areas of spurious gas regions being identified within the sort of bulk volume fluid. So we tend to get this slight behavior where we get a sort of increasing in gas, and then it kind of flows out, and then the gas starts going up again, and then we get a bit more flow. So we get this sort of rising as the sort of pressure rises, then it the sort of bubble sort of expands. We get a drop. Overall, the trend is matches the analytical results fairly well. So in future, what we want to start looking at is, as we showed earlier, we have some surface scan data of the initial sort of height of the Prepreg surface here. And then similar to what we've been doing before is want to put a sort of put a top plate on the top there and start compressing the fluid. So this is an initial sort of time simulation. So we start getting sort of higher pressures in this region here, where we're getting a sort of trapped bubble region there, and they resin in contact with the top surface. And then at the moment, the simulation sort of at the outer boundaries, we've got the sort of resin chamber pressure. So we've got a drop off in pressure there. So we still need to do a little bit of work on what outer boundary conditions we're going to apply for the pressure equation for the resin in this case. So that's what we're going to sort of look at in terms of sort of pure resin experimental data. But obviously, composites aren't pure resin. We have resin layers, and then we have fiber layers. So at the Bristol School, we've been working on a solid model for the fiber. So this is being done by a PhD student, Stefan Anderson. So as you saw, we get sort of particularly with corner cases, we can get large sort of curvatures in the ply layers. We need to be able to handle the case sort of, particularly if we've got sort of a void region where potentially we've got contact between the fiber layers, and then finally we've got to sort of couple this with the fluid equation. So in terms of the sort of structural model, 2D, the plies are represented by sort of particles connected by sort of rod elements, and then sort of have finite difference based approximation for the axial and bending forces across the connecting rods. And then this coupled to their ply layers. So even though sort of each ply is sort of has lots of fibers, they're sort of aggregated into one single ply layer. And then we apply a sort of finite influence region from the pliers onto the fluid. So the fluid is allowed to sort of use the flow through the fibers, but fibers introduce a sort of a Darcy based law sort of pressure force onto any resin flowing through the fiber layers. And then the same structural model for a fiber bag out to edge. And then we can initialize based on scans. So we have scan data showing where sort of void regions are within the fluid. So these can be either sort of in between the plies or corresponding to dry areas in the prepreg layers. So done some sort of initial proof of concept 2D FSI simulations. So the video on the left shows the sort of fiber and resin layers, and the simulation, it's the same simulation on the right that shows the response of the gas region. Yeah, so one thing to note is this is sort of 2D simulations, and we've got a very kind of coarse representation of the gas region. It does end up with effectively the gas being covered by the resin, because it can't sort of flow in and out of the sort of simulation in the third direction. So we do end up losing some gas mass in this, but that's probably due to the fact that this is just an initial low resolution 2D thing. But when you have sort of the high resolution gas region, it's less susceptible to this problem of mass deletion. So in summary, using implicit viscous terms allows us to greatly increase the time step compared to what we would be able to achieve just using explicit integration. We can use a background grid to model the gas phase without having to use all SPH simulation for that region. There's a little bit of work that needs to be done to smoothing out the coupling of the gas phase back onto the resin grid. And then we're working on a structural model to couple on to the fluid model to include the fibers in the overall model. So thank you very much. And any questions?
Thank you, Chris. Okay, so while we wait for some questions to come in, so I just wanted to ask, your solution is implicit, but it's, if I understand it correctly, it's also quasi-static. You've ignored any kind of inertia terms. Is that right?
No, the inertia terms are still in there.
Okay.
We have looked at removing the inertia terms, and we found that they don't make much difference to the solution at those viscosities, but likewise they didn't really. So main motivation for looking at removing them was to see whether we could further increase the time step size, but we found that it made very little difference to the time step size because their effect was small at those viscosities. So they're still in there.
Okay. And in terms of time step size or maybe CPU time, can you give us an idea how much faster this is for the time scales that you're looking at compared to if we were just using explicit time stamping?
Yeah, so I haven't sort of fully done the 3D case because there's sort of with the linear solve, it does sort of go up with the size of the problem. But in 2D, can't remember exactly the speed up. As I was showing, this 2D at sort of 100 Pascal seconds, we were getting a sort of time step of sort of 10 to the minus 2. For the explicit one, we needed a time step of about 10 to the minus 7. And then the nice thing about the implicit one is so that as you increase viscosity, turns out you could use a larger time step. The implicit one, as opposed to with the explicit one, as you increase time viscosity, your time step goes down. But so that was quite nice. But there is a kind of limit, even at higher viscosities, about the maximum time steps you can use, because then you end up sort of having a problem with the boundary. Essentially, you kind of the time step so large that sort of stuff starts sort of heading towards into the boundary. So that kind of there is an upper limit. But yeah, you get several orders of magnitude time step increase, but obviously you're spending more CPU time per time step. So I need to sort of go and redo that with the 3D because obviously it's the linear solve is going to take a lot longer in 3D.
Okay. I think I saw a hand going up, but
it was mine, but you asked my question immediately, so I put it down again.
Okay, sorry. So I don't know if there are any other questions. So I've got a few more actually. So
I have a question before you before you ask yours, if you don't mind, Tom. So I mean, obviously your hang on, from my face. Your applications here obviously are around composites manufacturing. What are the other applications that this framework could potentially be used for? I mean, it's obviously an interesting problem in itself, but where else could it go?
Well, it's sort of it's sort of anything that really needs sort of you to model a high viscosity sort of fluid. So yeah, there's so there's kind of the other sort of thing that I've seen sort of recently with people kind of looking at those sort of viscosity is actually sort of magma flow type things. The other people who do a lot of sort of high viscosity stuff tend to be sort of the sort of more the visual effects, sort of more your rubber things bouncing off each other and that sort of highly sort of deformable, almost sort of elastic kind of structures.
So my sort of leading question, if you like, from that was, most SPH codes, as we know, sort of tend to follow an explicit approach.
Yeah.
Are there any particular downsides to this approach if you were to just simply use this sort of formulation to do a typical fluid simulation?
So for a typical sort of fluid simulation, sort of if you were doing water or something, the big drawback would be, so what happens is with the explicit sort of simulations, as your sort of viscosity goes up, your time step goes down. But the implicit one is generally the other way around. So there's kind of this crossover point where the sort of time step size start sort of which one sort of where it becomes your implicit starts getting you higher time steps. So for the lower time steps, viscosities, typical SPH, you don't really get a larger time step size at those lower viscosities. So the big drawback for those then is essentially you've got this linear solve you've got to do each time step, and that can be quite, that's more expensive than the typical explicit kind of approach. Okay. So yeah, it is kind of limited to higher viscosity.
Yeah. So I wonder, it could be interesting as a to couple together.
Yeah.
Sort of more classical explicit SPH with this approach for problems involving both high and sort of more typical viscosity, some Newtonian and non-Newtonian problems in effect.
Yeah. Yeah, that would be quite interesting. Yeah.
Thanks.
Okay. Yeah, I've got a few more questions, and I think we can just seamlessly move into the discussion session. So I will. After seeing all the talks, it's if anybody's had some further questions on one of the earlier talks, this is an opportunity now to ask some further questions. So, but I would like first to stick with Chris's talk. So you described this model of interaction between the gas model on the background grid and the SPH particles for the resin. And in your drawings, the kind of the grid size, the background grid size was the same as the particle spacing. Is that also what's happening in the code, or is there a difference in the cell size for the background grid compared to the particle spacing?
So at the moment, it's a similar background grid spacing to the particle spacing. But yeah, that is one of the things that sort of, it's in the code that we can decouple the sort of the sizes. And that's one thing that's sort of on the list to look at. So yeah, so it doesn't affect the sort of gas model, but it's sort of getting the sort of overlap ratio, sort of volume fill on the background grid is a little easier when they're on a similar size. There's a little bit more of an error when you start having a sort of disparity in sizes between them.
Okay, and then for the kind of the final aspect that you described of the model, or actually what you plan on doing, this modeling the fiber layers in between and modeling the flow of the resin with the Darcy law through those layers. So are these layers rigid, or are they deformable as well?
So these layers are deformable. So yeah, so they're sort of modeled as points connected by sort of rigid elements which have an elasticity and a bending. So you can deform the layers as well.
But they're not SPH particles.
No.
Those layers are okay. Yeah. So it's a separate.
It's a separate sort of method.
Okay, and yet the SPH particles see that as a kind of a porous medium to
flow through. Yeah.
Yeah. Okay.